Good morning, Chem I. Today is the last day of Unit 12, or last information day. On this day, you'll have this video, but you'll also have a lab that'll be kind of the quiz for today. I know we've kind of been moving a little faster. I'm trying to get through as many things I can here before the end of the year, before when we have to stop instruction, just to make sure you're prepared. All right, so you can do it. Stay with me. Let me know if you have questions or you need to meet with me during office hours. That's completely all right. Today we're going to talk about something called equilibrium. Equilibrium is the idea that reactions don't just go in one direction. To this point, all you've ever seen is reactions where we say A plus B equals AB. And the assumption is that they're just heading in one direction. It's going that way. Today we're going to introduce the idea that reactions a lot of times are reversible. Most reactions are reversible, which means that there's a forward reaction taking place, but there's also a back reaction taking place. And this is based on how many things are colliding in space. Collisions are a key word here today. All right. So this would be how you would draw a reversible reaction. The production of ammonia is reversible. So we take nitrogen gas and hydrogen gas, and they will synthesize, as a synthesis reaction, to produce ammonia. At the same time, though, ammonia is decomposing back into N2 and H2. Well, you say, well, like, that's not very helpful. Like, you'll never produce what you're looking for, which is ammonia. You're still going to produce ammonia, all right? Just not as much as you'd hoped, all right? This is a big slide. Let's walk through it slowly. As we said, the key here is collisions. We call this kinetics, all right? Kinetics is the idea of motion, right? Things colliding. It's like a physics term. So in order for things to react, in order for an N2 molecule to react with an H2 molecule, they literally have to collide into another, okay? And the only way that that happens is if they're moving, all right? So there are things that we can do. There are ways that we can basically increase the rate of those collisions, all right? The first way is concentration. If we increase the concentration of N2 or H2, that's going to increase the rate of collisions, and therefore the reaction does what we call shift right, or increase the rate of the reaction, making more ammonia. Okay, it makes sense, right? If I dump more reactant in, it's going to more opportunity to collide, and it should produce more product. Temperature. If temperature decreases, the kinetic energy of the molecules decreases and the number of successful collisions decrease. You could flip this and write it the other way. If I increase temperature, molecules move faster, more likely to collide, more product. Next, surface area. If I increase the surface area or the particle size, the ability for the molecules to make contact increases. So typically speaking, the larger the molecule, the larger the surface area of the molecule, the reaction increases, we make more product. And then finally, a catalyst is a substance that, when present, improves the ability of reactants to collide, and therefore it will increase the rate of reaction and increase the product. Catalysts are kind of like these bystander chemicals that will create the opportunity for more collisions to take place. So those are the four things. We can increase the concentration, which will increase the product. We can increase the temperature, which will increase the product. We can increase the surface area, which will increase the product. And we can add a catalyst, which will increase the product. So all of those things are basically providing more opportunity for collision. All right, and those are the four. We call them stresses that you need to know, which gets to this, dynamic equilibrium. The idea of dynamic equilibrium, we told you that the reaction is happening in both directions, forward and reverse. Dynamic equilibrium then occurs when the forward rate of the reaction is equal to the reverse reaction. And when that happens, it appears as if the reaction is not, or nothing's happening, right? It's kind of we have a balanced seesaw is kind of an idea. This guy on the treadmill is kind of an idea, or the escalator, because he's running up in the same direction, or at the same rate as the escalator's moving him down. And therefore it looks like he's not moving. And that's what's happening with the reaction. So you have to have the forward and the reverse equal to one another. And this brings us to Le Chatelier's principle, which is where most of the work in this section is going to come in. Le Chatelier's principle says if we stress a system, or if we apply a stress to a system in equilibrium, that the system will shift left or right based on the response to that stress. And that stress could be anything that disturbs the equilibrium, like concentration, temperature, surface area, and so on. Okay, we will be dealing specifically with temperature and concentration here. So, the effect of concentration, the amount of substance in a system. If a substance's concentration is increased, the system must consume the extra amount faster rate, and the system will shift away from the added substance. Meaning, in this reaction, if I add N2, we're going to need to consume that N2, and therefore the reaction will shift this way, producing more ammonia. We call that a shift right, because after I add this new substance, we're going to shift to the right side of the reaction. If I remove a reactant, then it will shift toward the substance. So if I remove N2, it'll shift this way to fill this hole. I think about this, one of the analogies we use in class is I call hills and holes. If I build a hill somewhere, things are going to run away from the hill. And if I dig a hole somewhere, in other words, if I remove something from some side, stuff's going to run toward the hole. Keeping in mind that this right here, this reversible yield sign, is kind of the fulcrum of the teeter-totter here. Okay, so you should always be asking yourself, am I building a hill or am I digging a hole? And that's what we do with concentration. We'll get to the problems here in a second. Same thing with temperature. In order to know how a temperature is going to affect the reaction, you have to know which side the heat term is on. In an endothermic reaction, heat will be on the left. In an exothermic reaction, that means heat is exiting, or heat is a product, so heat will be on the right. All right? You must know that. And then it's just the same hill and hole. If we add heat to the one side of the equation that the heat is on, the reaction will shift away. And if we remove heat from the system, it'll shift toward the hole that we dug. And then catalysts, they always speed up the reaction. It speeds it up both forwards and reverse if it's at equilibrium, so nothing would happen. So this is the general rule of everything we just said to you. If a substance or heat is added, this system shifts away. And if we remove the substance or heat, it will shift toward whatever is removed. All right, that's the rule, but the general idea is, are we building a hill? Are we digging a hole? Okay, let's go through some examples, and I think it'll help you see what's going on. So here's a reaction. We got A, B, C, D. Typically, the way you see these reactions moving is because the products and the reactants are different colors. In the lab, you'll get to see one of these. So for instance, B here is orange and C is green. If my reactant or reaction or products become more orange, I know we're shifting to the left. And if they become more green, I know that we're producing more of C, and therefore I'm shifting to the right. All right? So it says predict the directional shift and color change. So if we add extra of substance A, we are building a hill at substance A. All right? That means we're adding extra substance A. And that hill is going to cause this to run away from the hill. Water runs down a hill to the other side. So we would call this a shift right, because it's shifting to the right side. And then it becomes, okay, what color are we going to see? Well, If it shifts here, that means we're making more of these. So what color are we going to see more of? Green. So it will become more green. They'll have less orange because some of that orange is going to get used up as it reacts with the extra colorless A. Let's say we place a system in an ice bath. We need to go back and I think read our instructions. It says, given this exothermic reaction, notice heat's not here. But if it's exothermic, that means there is heat on the product side. So then it's saying we're putting it in an ice bath. That's going to make the temperature come down. Okay, in other words, we are removing heat. We are digging a hole on the side that heat is. And when you dig a hole, guess what happens? Water runs toward the hole. So the reaction will shift toward the side we're removing from. This is also a shift right. And guess what? If we shift right, we're going to produce more green product. So this will become more green. Precipitate D is taken out of the system. So here's precipitate D. We're taking it out. So we're digging a hole. We're removing this from the system. And therefore, if we dig a hole, the reaction will shift toward the hole to fill the hole. Therefore, once again, it's shift right, and it'll become more green. Every time we shift right, we're producing more green product. All right? Finally, place the system in hot water. Oops, I erased my heat. If we put it in hot water, we are increasing heat, meaning we're building a hill on this side. That means it's going to shift this way. This will be a shift left. It's going to run away from the hill. And when it shifts left, it's going to produce more of this reactant here, which is orange. All right? You're going to watch a video in the lab that shows what this actually looks like. But this is how you do these problems. It's literally just deciding if I remove, it runs toward. If I add more, it runs away from. All right? Here's another one. This is what we'd call like a real problem here. This is an endothermic reaction. That means heat's going into the system. It says predict the following directions and how it affects the quantity of glucose given in the following conditions. So this is glucose right here, C6H12O6. So it says the system is occurring near a factory with additional carbon dioxide emissions. So here's my carbon dioxide, which means we have more carbon dioxide around, which is a hill. So we're just going to shift this way. So shift right, which means more glucose will be produced. As it shifts right, it's going to produce more of both of these products. The plant lacks adequate water. Okay, so that means there's not enough of this. So we're digging a hole, not enough water, and therefore it's going to shift toward that hole that we dug. So this would be a shift left, and therefore less glucose, because we're going to use this glucose to shift toward this way and fill that hole. Deforestation has removed oxygen from the trees. So that means there is less oxygen. We dug a hole, there's not as much oxygen. We're going to run toward the hole we dug. And therefore we're shifting right. And that's going to produce more glucose. It is winter. What's that trying to tell us? It's trying to tell us it's cold, meaning that we have less heat. We have a hole of heat, which means it's shifting toward that way, which means it's going to shift left and have less glucose. Okay? And that's it. That's all that we're covering today. It's just your ability to look at a reversible reaction and apply a little Chatelier's principle and ask yourself, which way will this shift based on the stress that we're applying to the reaction? That's all we're doing. When you get this done, take a look at that lab. The lab covers a little bit of everything from this section, and I think you should be good to go. Thanks for your hard work. Be good to somebody today. We'll see you soon.